Problem 577 of White textbook. Statement of the problem reads: a dam 75 feet wide with nominal flow rate of 260 feet cube per second is to be studied with a scale model three feet wide using Froday's scaling part A of the problem. What is the expected flow rate for the model part B? What is the danger of only using Frodday scaling for this test? Part C, derive a formula for a force on the model as compared to a force on the prototype. So before we start the solution, we need to understand about dimensionless parameters and what is Froday's number. Froday's number is a free surface parameter which is of huge importance, and it is named after William Frodday, a British naval architect who, along with his son Robert, developed the ship model, towing tank concept, and proposed similarity rules for free surface flows, such as ship resistance, surface waves, open channels. The Froude number is the dominant effect in free surface flows. It can be also important in stratified flows, where a strong density difference exists without a free surface. Froude number is defined as or given as Froude number is given as Fr is equals to U square upon GL. So this you can find it on table 5.2 of your textbook, which is on page 309. Basically, Froude number is a ratio of inertia to gravity. Inertia is represented as square of velocity to unit length. So that is inertia, and over here u square is your velocity square divided by length, that gives you inertia, and whole divided by gravity gives you the ratio of inertia to gravity provides you Froude number. Okay, let's proceed further with the problem. So what are we given? For part A, we are told what is the expected flow rate for the model. So we are given length of the prototype is 75 feet. Length of the model is 3 feet. Flow rate of prototype which is represented as Q, flow rate is represented as Q of prototype, is equals to 260 feet cube per second. Using Froude number, let's say the Froude number over here, the subscript P is for prototype and is equals to Froude number, and the subscript M would be for model. And we have written like this. Froude number is represented as U square upon GL whole of P is equals to u square upon gl whole of m. That can be written as implies u square p divided by gp lp is equals to u square m divided by gm lm. gp and gm are basically, in both cases, be it prototype or model, it's the acceleration due to gravity, which can be taken as g. So we can say, since gp is equals to gm is equals to g, they get cancelled on either sides of the equation, and hence we are left with the equation as u square m by cross multiplying, you bring p onto the u square p onto the right hand side. It should be u square m by u square p is equals to lm upon lp, which implies um upon up would be equals to lm upon lp whole square root. This given conditions, lm was 3 feet and lp was 75 feet. Let's, which implies um over up is equals to, what was the, as per our substitute them over here, that would be 3 feet divided by 75 feet, everything under root, so that 325 times, which would be equals to 1/5. So that implies um upon up is equals to 1/5. From that, since we know the ratio of velocities of model to prototype as 1/5, we can use it to calculate flow rate. So flow rate Q is equals to velocity of flow multiplied by cross section area, which implies, if we have to calculate the flow rate of model, which will be Qm, would be velocity of the model multiplied by cross sectional area of the model. And similarly, flow rate of prototype would be equals to velocity of prototype multiplied by cross-sectional area of the prototype. Area of the model would be equals to square of the length of the model, and area of prototype is equals to square of the length of prototype, which implies ratio of flow rate of model to flow rate of prototype would be equals to velocity of model by velocity of prototype times area of model by area of prototype. From this, we do know the ratio of velocity of model to velocity of prototype is 1/5. That is 1 by 5 times area of model upon area of prototype will be square of length of model by length of prototype square. So rewriting this, it can be written as 1/5 times 3 feet square by 75 feet square. Which comes out to be, after calculations, it comes out to be ratio of Qm upon Qp, that is flow rate of model to flow rate of prototype, is equals to 1 divided by 3125, which implies model flow rate of model to flow rate of prototype is equals to 0.0032. We are told to calculate what is the flow rate of the model, and we do know the flow rate of prototype, and since we have developed a relation over here for flow rate of ratio of flow rate of model to flow rate of prototype, we can derive here, which implies Qm, or flow rate of model, divided by flow rate of prototype is given as in the problem 260 feet cube per second, is equals to 0.0032, which implies flow rate of model would be equals to 0.0032 multiplied by 260 feet cube per second. So which implies Qm is equals to 0.0832 feet cube per second. That's your answer for the flow rate of the model. Next, we try to solve part B of the problem. Part B of the problem says, what is the danger of only using Froude scaling for this test? So the problem would be with such a small model and flow rate, there may be viscosity and surface tension effects that is perhaps the Reynolds number and Weber number are also important. So that's the answer for the reason if we only use Froude scaling for this test. Part C, derive a formula for a force on the model as compared to a force on the prototype. So from equation 5.1, page 301 of your textbook, F or force is function of rho v L. F in dimension form is F is equals to ml t power minus 2. That's your LHS. Now we have three variables on your right hand side which are dependent as a function. So first variable is rho, which is density. That is equals to ml power minus 3. We have v, which is velocity. That is equals to L t power minus 1. And last but not the least, L is length, which is equals to L. And these form your RHS. Now we need to arrange LHS and RHS dimensions in such a way that they both are equal. Implies your LHS was ml t bar minus 2 is equals to your right hand side is ml power minus 3 whole power a dot l t power minus 1 whole power b. And last but not the least, L to the power of C. So if we do that and rewrite it, it can be written as m to the power of a, L to the power of minus 3a plus b plus c, and t to the power of minus b would be equals to m l t power minus 2. Now equating the bases, the powers, we get a equals to 1. So minus 3a plus b plus c equals to 1, and minus b is equals to 1. Oh, sorry, minus b is equals to 2, which implies b is equals to minus 2. So that you have two of them. When you substitute them in the second equation, you get minus 3 times 1 plus of minus 2 plus c equals to 1, and that gives us value of c is equals to 2. Now when you substitute these a, b, c values into the previous equation of rho v l, we get rho of to the power of a, which is m l power minus 3 whole to the power of 1 v l t power minus 1 whole to the power of minus 2 sorry, my mistake. Minus b is equals to minus 2, and this would be plus 2. So over here it would be plus 2. And last but not the least, it would c is l raised to the power of 2, and this is rho, this is v, and this is l. When you see rho to the power of 1, v square l square, this will be equals to m l power minus 3 times l square t power minus 2 times l square, which after you do the calculation of dimensions you get m l t power minus 2. and this was your RHS, which is your force. That is satisfied. Now, force of model to force of prototype would be equals to rho of model divided by rho of prototype times velocity of model divided by velocity of prototype times, this would be whole squared, times length of model divided by length of prototype whole square. Since we are dealing with the same liquid, so density of liquid is same for model or prototype. That means rho m is equals to rho p is equals to a common density rho. So that when we substitute rho over rho becomes 1. So that would be Fm over Fp is equals to 1 Vm over Vp square would be 1/5, which we got it in the previous calculation where we had ratio of velocities in the previous steps where we calculated in part A. So that is 1/5 whole square multiplied by length ratio is also before square root it would be 1/25 whole square, and this gives us implies Fm over Fp is equals to 1/25 square into this would be 1/25, so that would be 1/25 whole cube, which will be equals to 1 over 15625. So that implies Fm over Fp would be equals to 0.000064. Further it implies to us that Fm would be equals to 0.00064 Fp, which states Fm is extremely small than Fp. That's our final answer. If you have any questions related to this problem, you are free to ask me. Please go through it. If you have any questions, feel free to ask me. You can email me, or I am available on Microsoft Teams. My email is slanka@uwm.edu, and you can text me or you can call me on Microsoft Teams and ask your questions. Thank you.